Hello and welcome. The Generate the Surface Mesh task in the Ansys Fluent Meshing watertight geometry workflow is used to generate a mesh over the surfaces of an imported CAD geometry or remesh an imported surface mesh. Surface meshes define the boundaries of the computational region or volume for the CFD analysis and lay the foundation for generating a high-quality volume mesh for CFD analysis. In this lesson, we will discuss about some of the important inputs under the Generate the Surface Mesh task and the different size functions available. We will also understand the influence of local and global size controls on surface and volume mesh before ending the lesson with a discussion on improving surface mesh quality. So, without further delay, let's get started. Launch Ansys Fluent in meshing mode. Under the drop-down menu in the Workflow tab, select the watertight geometry workflow. In the Import Geometry task, keep the options to default and load the provided CAD file. The model we have here is that of a printed circuit board placed inside an enclosure which acts as a fluid region. Two cylindrical capacitors as well as heat sinks are embedded on the PCB. We will not be adding any local sizing and will continue to the Generate the Surface Mesh task. Note that the inputs given in Generate the Surface Mesh task will apply globally. Since we are not using any custom size field or control files, let's leave the setting to the default no and move on to the minimum size and maximum size inputs. These inputs specify the minimum and maximum sizes respectively of the elements for the surface mesh and are pre-populated by default based on the size of the bounding box for the domain. In most cases, these default values are sufficient to generate a good surface mesh. However, users can change these values as needed. Care should be taken to set the minimum size small enough to allow resolution of smaller CAD features of interest. It is important to ensure that the model is properly scaled by selecting the appropriate units during the import. When we click in the field, small red-colored mesh size boxes show the preview of the field value on the CAD entities. Let's change the minimum size value to 0.03 mm and move to maximum size input. The value of maximum size depends on the geometry you are meshing. Ensure that the value is not too large to result in loss of accuracy in resolving large CAD features and flow characteristics. We can vary the min and max sizes to refine or coarsen the surface mesh. Let's change it to 1 mm. Next comes the growth rate, which defines the rate at which the surface mesh elements increase along each successive layer. To understand the growth rate better, we will compare three surface meshes and growth rate values 1.05, 1.2 and 1.3 respectively. Lowering these values closer to 1 would achieve a finer mesh resolution further away from the boundary. But this refinement comes with a heavy increase in the overall computational cost. Increasing the growth rate values beyond 1.2 will coarsen the surface mesh and must be used with caution. Growth rates value greater than 1.4 should be rarely used. Let's keep the default growth rate value as 1.2. Next, let's understand the size function input. For this input, there are three options: curvature, proximity, and curvature and proximity. For brevity, we will directly discuss the curvature and proximity option. The curvature and proximity size function option requires three inputs from the user. The curvature normal angle is associated with curvature size function, and the other two inputs, that is cells per gap and scope proximity to, are associated with the proximity size function. The curvature normal angle dictates the maximum allowable angle that one element edge may span the geometry curvature. For example, a value of 10 implies that a division will be made when the angle changes along the curve is 10 degree, and therefore a 180 degree arc will be divided into approximately 18 segments. A smaller normal angle generates more refined surface mesh. Cells per gap function ensures the presence of an appropriate number of cells in gaps as prescribed by the user through the cells per gap input. Here, the gap is defined in two ways: the area between two opposing boundary edges or a face, and the internal volume between two faces. Let's change the value to 3. We can use this option under the scope proximity to set scope to proximity based refinement. In this demo, we will set the scope to faces. For visualizing the influence of different size functions and scope proximity to inputs on surface mesh, please refer to the lesson on the Add Local Sizing task. Click on Generate the Surface Mesh button to confirm the inputs and execute the task. We will now generate the volume mesh by following the steps shown. For brevity, we will skim through these steps. Once the volume mesh is generated, save the mesh as mesh-1. Now let's understand the use of local and global size control. Click on the Add Local Sizing task and change the answer to Yes. It is crucial to remember that the purpose of adding a local sizing is to refine selected geometric entities or regions. We can see that the status of all the other tasks below Add Local Sizing changed to incomplete. Now change the size control type to curvature. Select the label wall capacitor 1 and wall capacitor 2 as highlighted. Change the local min size to 0.03 mm and max size to 1 mm. Set the curvature normal angle to 10 degrees and leave the scope to field to its default setting, faces. Click on the Add Local Sizing option to complete this step. Let's also add the proximity local control. Select the wall heatsink 1 and wall heatsink 2 label and use the same min and max sizes as previously done for the curvature setting. Change the cells per gap to 3 and leave the scope 2 setting to faces. Let's hit the Add Local Sizing button at the bottom and move to the Generate the Surface Mesh task. Change the minimum size to 0.3 mm and maximum size to 8.5 and select the curvature and proximity size function. Retain the default curvature normal angle and cells per gap values of 18 and 1 respectively. Although the parameters that control the global size functions are the same as the local, it is important to understand that these settings are applied globally on all surfaces of the CAD except on those entities where we have prescribed local size controls. Keep all the other inputs as it is and hit Generate the Surface Mesh to generate the mesh. Once the surface mesh is generated, follow the same steps as that of Mesh 1 to generate the volume mesh. Once the volume mesh is generated, save the mesh as Mesh 2. Now we have two meshes, one where only global sizing was applied and other with both local sizing and global sizing. Upon inspecting the two meshes, it is very clear that the inputs in the Generate the Surface Mesh task have a global influence, that is on all the surfaces, whereas inputs in the local sizing task are localized to only the selected entities. The refinement obtained in Mesh 1, which results in nearly 2 times the number of cells as Mesh 2, may be appropriate for a few regions but unnecessary for other regions of the model. Such unnecessary refinement is not desirable as additional computational resources are required not only during the meshing stage but also while solving the problem. Please note 2 key points here. First, it is always a best practice to employ the local controls for refining the mesh for selected CAD entities, and the global size controls can be used to generate a coarser mesh on all the other surfaces. Second, the small sizes always take precedence over the large sizes irrespective of whether they are local or global controls. Next, let us understand what surface mesh quality is and how to improve it if it is necessary. Let's import a different geometry for better understanding. We can see that Add Local Sizing task is already completed, so let's move to Generate the Surface Mesh task. Set a minimum size to 20 mm and maximum size to 400 mm. Keep the rest as default and execute the task. Once the surface mesh is generated, a warning message is printed in the console. The maximum skewness value is 0.95. Skewness is the default quality measure used. It determines how close to ideal a cell face is. For triangular elements, this means how close to an equilateral triangle the element is. A skewness of 0 indicates an equilateral element, while a skewness of 1 indicates a degenerate element. Bad quality surface mesh can result in low quality volume mesh that can cause convergence issue during simulation. It is generally recommended to keep the surface mesh skewness to below 0.7. Let's now try to improve the surface mesh quality. Right-click the Generate the Surface Mesh task to open the context menu. Go to Insert New Task. Keep the limit value as default and execute the task. For most cases, just performing the improve quality operation should be sufficient to bring the quality within acceptable limits. However, in this case, the maximum skewness is brought down to 0.85. The problematic areas left are now highlighted to help diagnose the problem. The quality of the cells on the trailing edge of the wing was too poor for the improvement process to be successful. For such cases, the best approach to improve the mesh quality is to add additional local sizing control to improve geometry capture where necessary. Click on the last local sizing and select Revert and Edit. Click on Add Local Sizing. Add a face sizing with a target mesh size of 1 mm. Select the label as shown and complete the task. Select Yes on the pop-up message. Now, generate the surface mesh again. The mesh quality has greatly improved with a maximum skewness value of 0.7, which is within the recommended range of skewness. For this reason, the separate mesh quality improve task is no longer required and can be deleted. So, let's recap what we learnt in this lesson. We learnt about the different inputs under the Generate the Surface Mesh task. We discussed the influence of local sizing controls as opposed to that of global sizing controls. We concluded by discussing about how to improve the surface mesh to achieve good volume mesh. That brings us to the end of this lesson.